Welcome to The Explainer. Today, we are literally peering behind the curtain of the apps you use every single day to look at the Geographic Data Processing module. We're going to uncover the hidden mathematical matrix that powers modern cartography and transforms our messy physical world into pristine digital logic. Just look at this beautiful textured globe. This isn't just a pretty picture, right? It actually represents a massive, complex database of spatial coordinates, elevations, and themes. Modern cartography is all about analyzing this incredibly dense geospatial data to guide everything from urban planning to vital environmental conservation. So here is our roadmap for today's boot up. We'll start with the geometry of space, then classifying data, data fusion, topological networks, and finally, tracking change over time. Let's kick things off with Module 1, the geometry of space and physical dimensions. We have to start with the foundational building blocks of geographic space in 2 and 3 dimensions. Take a look at this. It brilliantly illustrates a fundamental geometric concept called compactness. Notice the square and the narrow rectangle here? Both actually share the exact same area size of 16 square units. But mathematically, the square is highly compact, scoring a 0.79, while that stretched-out rectangle gets a measly 0.17. In spatial analysis, shape dictates function. A perfectly compact forest behaves very differently ecologically than a long, thin strip of trees. And hey, this isn't just flat. Algorithms use similar geometry to calculate 3D volumes, like figuring out the total water capacity of a reservoir, or mapping the actual three-dimensional volume of a city skyline. Now, when we're calculating areas and enclosing data points, we also use a concept called convex hulls. Imagine taking a giant digital rubber band and just letting it snap tightly around the outermost points of a collection of geometric objects, kind of like the neighborhoods and forests you see on the right. This essentially acts as a digital perimeter fence, defining the total territory of a scattered dataset. It's absolutely crucial for determining things like the absolute boundaries of a brand new subdivision or a protected wildlife habitat. Moving right along to Module 2, classifying thematic data. This is where we give space meaning. We take that raw geometric space we just defined and we assign it real-world context. Because let's face it, raw geodata is often just too complex. Reclassification reduces the noise. Check out the original map on the left. It's totally filled with hyper-detailed categories like swamp and agriculture. By reclassifying, we can simply merge those into a single clean, undeveloped layer, while rolling residential and commercial into a built-up area layer. We're simplifying the matrix so human beings can actually make sense of it to make big-picture decisions. Okay, this is where it gets super fascinating. Look at how different mathematical choices completely change the visual narrative. This is population density across Germany. A quantile division, which puts an equal number of states into each class, presents a very different visual story than natural breaks, which groups values based on the inherent data clusters. The exact same raw data tells entirely different geographic stories depending entirely on the math we apply to group it. We do have to be careful, though. Purely data-driven classification can accidentally hide vital information. Say a region contains a local maximum, like one incredibly expensive neighborhood completely surrounded by cheap ones. Well, a generic classification might just lump it in with its neighbors, completely erasing it visually. That's exactly why modern systems use spatial relationship tools, like the Geodata statistic, to explicitly preserve and highlight these vital spatial hotspots. All right, Module 3, combining geometry and themes. This is all about data fusion, and we'll see how things build when we fuse physical geometry and thematic meaning together. This right here is where the real power of spatial analysis unlocks. By geometrically superimposing layers, we can use Boolean logic to answer complex questions. Look at this overlay process. If we have a geometric layer of forests and another layer for rivers, we can run a logical AND intersection. The system instantly isolates only the specific segments of the river that flow directly through the forest. It's highly targeted data fusion. But what happens when your spatial units just don't align? See, we have data by zip code, but we desperately need it by school district. Well, through areal interpolation, we can mathematically adjust the units. We can aggregate small units into larger ones or disaggregate large units down based on percentages or absolute values. It basically forces incompatible data to finally speak the exact same spatial language. And this kind of combined geometric and thematic fusion is exactly how urban planners generate practical safety zones using a technique called buffering. The system can calculate a strict 50-meter buffer zone tracing the exact path of a gas pipeline, or a 400-meter protective zone around an irregularly shaped nature reserve. It's literally using geometric data to enforce thematic rules out in the real world. Next up, Module 4, Topological Networks and Connectivity, affectionately known as the rubber skin. This is a fascinating space where exact physical coordinates matter far less than how objects connect to one another. So, topology is often called rubber skin geometry. Just imagine our digital map is printed on a highly stretchable rubber sheet. You can stretch it, you can compress it, or twist it all you want. The exact physical distances and angles will radically change, for sure, but the essential topological properties, like what is connected to what and what neighbors what, remain completely intact. To understand why this is so incredibly useful, think about a routing query from London to Liverpool. When your GPS calculates the fastest route, the algorithm absolutely does not need every exact latitude and longitude coordinate of every single curve in the road. It only needs the topological network. It needs the nodes, which are the intersections, the edges, which are the road segments connecting them, and the thematic weight of those edges, like travel times. By stripping away all that exact geometry, the system can calculate your route in milliseconds. And topology isn't just for road networks. It also defines vital neighborhood relationships. Notice a difference in the data models here. In a vector model of polygons, neighbors might share a direct boundary edge, or maybe just share a corner node. But in a raster model, which is made of grid cells, neighborhoods are defined by the surrounding pixels. Understanding these hidden topological rules is exactly how software determines what objects influence each other in space. Finally, we hit Module 5, Tracking Temporal Change, Geodata in Motion. This is where we activate the temporal processing module to track how all these geometric, thematic, and topological properties shift over the dimension of time. Because mapping geodata in motion is super complex, algorithms analyze time in 3 progressive steps. First, you have a time-slice query, which is looking at a fixed moment in a constant space. Think of checking unemployment in the year 2010. Second is a time window query, analyzing a range of time in a constant space, like tracking unemployment changes in London from 1950 to 2000. And finally, the really tricky one, the moving query. This analyzes a time range within a variable space, such as tracking population within the ever-shifting borders of the European Union. And when we look for massive existential changes, like a dense forest being completely chopped down and suddenly becoming a built-up city block, we really have to map that transition. We contrast bitemporal change, which compares just 2 static points in time using simple difference maps, against multitemporal change. That requires complex flow maps and transition matrices to track continuous geographic evolution across many points in time. So, as we complete our system diagnostic of this incredible geodata matrix, we've seen how geometry, themes, networks, and time are perfectly woven together to map our reality. But I want to leave you with one final, kind of wild question to ponder. If our algorithms and cartographic systems can capture the past and map the present with such stunning, layered precision, how long before they can calculate and render the exact future topography of our world? Thank you so much for joining me on this explainer, and keep questioning the data around you.